1 minus x sub 2 squared plus y1 minus y sub 2 squared plus z1 minus z2 squared. There we go. That's what we're trying to minimize shortest distance. What's the constraint though? Look through the problem. There's got to be some constraint under this.
That point.
Yeah, this whole idea of this plane right here. I mean, a point's going to come into play here. We'll put the point in there. There's your constraint. Because it's a point on this what? That point just can't be anywhere. The point we're talking about has to be on this plane. So that's your constraint over here. We're trying to what? This is what we're trying to minimize. That's the function you're trying to minimize. This g over here is just a constraint. It's got to be constrained to that plane x plus y plus z. So you can write g equals x plus y plus z. You know, you got to put the equals 1. You can put that, you know, in terms of that. But this is really what you're going to take the, you make the gradient of this. So I'll just put, I'll write this. I'll say this is our constraint. You can set it equal to g if you want. But this right here is g of x, y, and z. That's your g. Now, where are we plugging this point? In there? So I'm going to write it again. X minus what? 2 squared plus y minus 0 squared plus z minus.
Plus.
Yeah, that when I got a 2, 0, negative 3 here. Alright, it says make that z plus 3. So far, so good? There's your f, there's your constraint. We're going to get some gradient vectors in a second. I do want to point something out. Do you recall this from Calc 1? That when it comes to minimize or maximizing distance, you can just minimize or maximize distance squared. You get the same answer. If you want to avoid that radical. Did you know that?
Mm-hmm.
You can definitely do it. So I mean, if you want to deal with the radical, you can. It's just going to make your derivatives a little bit harder because of the radical. But you can totally maximize or minimize big distance squared. And we just think of this as what? Same thing goes if you tried this in section 14.7. This just allows us to avoid the radical. If you didn't know that, when it comes to finding in terms of maximize or minimizing distance, optimization, you can maximize or minimize distance squared, you get the same answer. If you want us to prove it, we can. We can do some little implicit differentiation. You know, you just would divide that thing out in the end. It wouldn't factor into the problem at all. So when here's our function right here. There's our function of x, y, and z. There's our constraint. So our first step is, what's step 1? You got to find del f and del g. And in front of del g, I want you to put the lambda symbol. All right, so what's del f? Which in this case, I don't care if you call it del. Do you want to call d squared now f? All right, so what's del f? Don't we make a vector? That's a vector. Gradient of a function is a vector. Well, it's made up of all the partial derivatives. Fx, Fy, and Fz. What's with respect to x? Partial with respect to x. All that mess. The beauty of this section, everyone, you don't have to substitute a z like we did last time. Remember that? But if you did want to work this problem by 14.7 technique, you would have to replace the z with something. Could you do it? See, that's what I mean. You can do this problem, like even on a test, you go, I'm not sure I'm going to use the technique from 14.7 to solve this. By all means, you could. But you'll see a nice elegant method here too as well. This is just what, 2 times, and that's it. What's this derivative? Partial derivative. And this is just 2 times e plus 3. Is everyone agree? Those are the partial derivatives. Now come over here. What's del g? Oh, and put a lambda in front of it. Lambda del g. All right, what do we get here? That means I'll put del g down, then I'll just distribute a lambda everywhere. I can put this in. They share the common gradient vector. This is easy. What's their respect to x?
1, 1, 1.
This is what makes this technique easy. A lot of times you're constrained. You get those partial derivatives, you go, oh, these aren't bad at all. Now you have to distribute the lambda to all of them, so this is one what? One lambda, one lambda, one lambda, so I'm just distributing it. This is what we do. This is the system we gotta solve. Solve this system. Now if we get more than one answer, all we have to do with our, say we got 3 answers, we'll just check them all to see which one gives us the shortest amount in terms of distance. Go back to the distance rule. But if we only get one answer, I'm pretty sure that one answer is it. Do you agree? There you go. So that's the idea. You go, what if I got 4 answers? In the final step, just take all 4 answers and see who wins. Put them back in the distance. We got to solve this system. Now this is what happens with Lagrange multipliers. Your system is set this equal to this. Corresponding components, set this equal to this. Set this equal to this, and then there's one more thing. We got to list the constraint. Alright? So I'm going to do this. Here's the system we got to solve. What's 2 times x minus 2? What's that got to equal?
1 lambda.
1 lambda. I'll put and. What's the next part? 2y must equal
1 lambda.
lambda. And 2 times z plus 3 must equal the.
Same.
This is the biggest error. I've taught this for years, everyone. Even students would have like the technology to solve this. You know, like a TI Inspire where it has a solve system button. And it comes out not working out because they forget to list the last constraint. You always list in your system the constraint for your problem. What's the constraint? Always add that. You can do it at the beginning or at the end. What's my 4th thing? This is the system of equations you're solving right here. It may look long, but it's not that bad. We're step away. We're a couple minutes away from getting this thing solved. All we got to do is solve that system. So this equivalent to this one. This one equals this equals this, and this. So we got 4 equations. How many variables? X, y, z, and lambda. But we'll still solve it. Still solve it. Alright, so we got to get started with this. Let's see. What do y'all think, everyone? I could solve for x here in terms of lambda. I could solve for y here in terms of lambda. Was it lambda over 2? I could solve for z here in terms of lambda and substitute them all in here and everything would have lambdas. And once we get lambda, we can get all the numbers. Let's do it. So 2x minus 2 distributed equals lambda. What would x equal? 2x minus 4 equals lambda. What's x? Lambda plus 4 over 2. Did I do it right? Yeah, I'm not. Thank I need to back me up. Thank you. What's y equal to?
Lambda over
2. Alright, what's z equal to? I gotta distribute this first. 2z plus 6 equals lambda. So z equals lambda minus 6 all over. You ready to jam it in here? Lambda plus 4 over 2 plus lambda over 2 plus lambda minus 6 over 2 equals 1. Boy, we solve that, got lambda, we're going to have this thing solved up. We'll plug it back in here. Got them right here. All ready. All we need is lambda. You want to multiply 2 on both sides? Multiply 2 on both sides, and then get your common like terms. So if I multiply 2 on both sides, those 2's are gone. But this turns into 2. What's lambda plus lambda plus lambda? 3 lambdas. What's 4 minus 6?
-2.
And I now have 3 lambda minus 2 equals 2. So 3 lambda equals 4 with lambda.
4/3.
And now I'm smiling because all we gotta do is put that in there, here, and here, and we got x, y, and z, we get the point. Because they find the point on the plane, we'll get it. Let's see what it is. What's x? Well, you don't mind fractions here. What's 4/3 plus 4 over 2? Y, what's 4/3 over 2? Feel free to use technology if you don't like fractions so much. What's 4/3 minus 6 over 2? Those 3 numbers are going to be the point. 4/3 plus 12/3 16 thirds over 2. 16 over 6, what's that reduce to?
8/3.
Is that 8 thirds?
Mhm.
Someone hear that? What's y equal to?
Two
Y
thirds.
equals 4 thirds, divide 2. 2 thirds?
Mhm.
Let's see. What's 4 thirds minus 18 thirds? What's negative 14 thirds over 2?
Negative 7/3.
Negative 7 thirds. Yeah, I always worried I make a little arithmetic error where you term, pre-algebra in terms of like adding and subtracting fractions. So I want to check this. Does that make this statement true? That one right there? Do these all add up to 1? Because it's got to be under that constraint. I mean, it definitely has to be all add up to 1 here. 8 thirds plus 2 thirds is 10 thirds. 10 thirds minus 7 thirds is 3 thirds. Yeah, we're good. Now that's the point on the plane. There's the answer. This is the point on that plane, x plus y plus equals, that has the shortest distance in three-dimensional space to that point. Shortest distance. Isn't that cool? Hey, actually, the problem out of the book, if you're curious, they wanted you to find the distance. I reworded it like this, but what would you have to do if you had to find the distance? What would be the last step? Just plug it in here. I just think it saves time, especially on a test. Just to say, get the point. Because I knew you could plug it into the distance formula. So, and keep in mind, you could have used 14.7 technique. I do like a problem like this, seriously on a test. Many times I like to give you that option. You can do it by this method or by that method. If you did 14.7 technique, the only thing you had to do was what here? You wouldn't have had this, in terms of F, you wouldn't have like gradient vectors. You would just replace the Z in terms of solving right there, what is Z equal to? 1 minus x minus y, that's what we've done that section. You would have taken this and what? You had a function of x and y. Cool. Alright, hey, last problem. Let's look at another one of these. So, that was number, you want to know which problem that was number 39. But it wasn't in 4.8, it was in 4.7, because in 4.8 they had to go back to 14.7 to work the same problems. Because they're trying to show you that you can use either technique to solve it. So this is number 47 from section 14.7. Find the volume. Okay. Find the volume of the largest rectangular box. All right. Optimization. Largest rectangular box. In the first octet. With 3 faces in the coordinate planes. All right, with 3 faces in the coordinate planes. And 1 vertex in the plane x plus 2y plus 3z equals 6. All right. I always like to look at this problem. I'll start drawing some pictures and stuff. I like to look at it. Figure out what's that F and what's the constraint. So what are we trying to optimize? Maximize and minimize. Volume, very good. That's what we're doing, the volume. We're trying to optimize volume, we're trying to get the largest volume, maximum volume. So where's the constraint? It's almost like you can go, oh, this is the other equation, yep. This is one equation, there's my constraint. That's my G, right there. Because one vertex has to be in that plane, right? Constrained to that plane. It wasn't like, oh, that vertex can be anywhere in quadrant 1. Exactly. So, if you want, we can even draw a picture. Because they said this thing's in quadrant 1, or octant 1. Picture always helps. We're just going to draw a box. Do you remember how to graph that plane? Like, what would be the x of it?
1.
6?
Oh, 6, yeah, yeah.
All right, 6. I'm going to put 6. What's the y intercept? 3. And 2. So there's that plane, but I'm only saying only one point of the box can be in that plane. So this box may look something like this. It may not be big. But it might be a box like this. I'll draw it like this. And you're talking, your box might be just that big. Like one face on this side, one face on this side, but one of the corners is sitting at what? That ramp coming down, that plane. That's what's happening here. So it's the idea of like, okay, I'm going to have one face over here, one face over here, but it's going to come up, and that corner of that box is going to hit this portion of that plane, that triangle there. Well, that picture doesn't have to be perfect. The key is, I can draw this box bigger. What two variables you want to use? You want to use x, y, and z? I like that too. X, y, z. Sound good? So I'm going to start out. V of x, y, and z is x, y, z. That's the function you're trying to optimize. What's the constraint? Our constraint is
X plus 2y plus 3.
x plus 2y plus 3z